Hello, so I'm Pierre. I'm the CEO and co-founder of C12. I'm very happy to be physically present because it's my third time at Q2B, but actually my first time in person. The last two times I had to be attend remotely. So finally in 2022, I breast this attending remotely course. C12, we are leading the next material leap, and we are building the future quantum processors. So first, who we are, then our vision, and also what is very unique about our approach. And I will also share our latest tech results, including teasing a world record, and we are very proud of this. And last, our product roadmap. So C12, we are a Paris-based quantum hardware startups. We are a spin-off of the École Normale Supérieure in Paris. In 2020, we found C12 with actually my twin brother, with also our CTO. Our portfolio is now 6 patents. We are backed by deep tech investors, but also corporates like Airbus and BNP Paribas. And we are now 30 people, including incredibly talented engineers and quantum physicists. And we are focusing on building quantum processor first for application in quantum chemistry. So quantum computing will transform, and I fundamentally believe this, our society and our industry, because it can solve the world's most complex problem. So why do we not have quantum computers? So we don't have quantum computers yet because quantum actual current hardware are with a very too high level of errors. We don't have them yet because actually these errors, they increase when we scale the numbers of qubits. And we don't have them yet because we are optimizing current approaches without having the right material. Because the fundamental challenge of building this quantum revolutionary machine is that quantum material interact very easily with their environment. And this is a simple fact. All errors, they're coming from defects in the qubit material. No defects means no perturbation of the qubit, and no perturbation means no error. And there is actually a quite large consensus in the scientific community and in the quantum industry about this fact. A review in Science stated materials issue will be critical to be addressed in the coming years. And I also picked one quote from a great scientist I admire, Chris Monroe, who is also a chief scientist officer and co-founder of INQ. And what he's saying is that if we want to build a large-scale quantum computer, we need a breakthrough in the material. And this materials leap can be carbon nanotube. So at C12, we use this elementary and ultra-pure material to build qubits. They have extraordinary properties because they kind of solve the quantum paradox. So we can make qubits out of them that are both isolated, but yet addressable. So this is the most minimal electrical wire you can imagine, and we are transforming them into quantum transistor. What I think is that carbon nanotube can be really the form factor of next generation quantum computers. What was supposed to be hard about carbon nanotube is the fabrication process. And on this, we patented a nano-assembly fabrication process where the carbon nanotube are dropped off on a silicon substrate at the end of the fabrication process. And these suspended carbon nanotube are hosting a single electron, and we manipulate its spins to make a qubit. So silicon made possible the emergence of the classical computing. It's time for carbon to do the same with quantum. So how are we different from other and what is unique about our approach? So to implement a quantum algorithm, we need a large number, this is the x-axis, of good quality qubits. What is great about atoms and ions and their qubits lie in vacuum. So they are well isolated and they benefit from long current time. But they face also fundamental challenges to scale above 1,000 qubits. What is great about on-chip technology like superconducting qubits is that they are much easier to scale because they benefit from semiconductor fabrication techniques, but they are reaching their limit in terms of coherence. C12, we kind of combine what is best in both worlds. The manufacturability of semiconductor devices with this ideal architecture of a spin qubit in vacuum. Because at the end, our spin doesn't see anything else than a couple of hundreds of very pure carbon atoms. So what is unique about our approach is unparalleled fidelity, scalability, and connectivity. So on the fidelity, we achieve this because we have this ultra-pure material that protects our qubit from errors. On the scalability, our fabrication process is compatible with industry-proven semiconductor fabrication techniques, and our nano-assembly techniques enable versatile design. So with this high connectivity, we can reduce the number of quantum operations, so the circuit depths, and also reduce the overhead needed for error correction. Where are we in terms of qubit quality? So there are three sources of errors, three decurrence channels. It could be magnetic, it could be electrostatic, and it could be phononic, so with coming from vibration. And on all of three of them, to our knowledge, there is no other solid-state platform that can achieve what we have in carbon nanotube. So we set really world records on all of them. On the magnetic part, the noise comes from a nuclear spin, and because we have isotopically purified carbon nanotube, we can actually reduce this noise level to 2 orders of magnitude compared to silicon. On the charge noise, and this is a very new result, and I'm very happy to share this with you, we actually measure the lowest sensitivity ever to charge noise in a suspended carbon nanotube. And this is because it's suspended, and we achieve 2 orders also a magnitude less than silicon CMOS qubits. And the last is about phononic noise or vibration. And because we have a 1D structure, we have confined phononic mode, and we can uncouple from them. So the race to build a quantum computer is extremely hard. But what we think is that the race doesn't look the same if you start with the right solution at the beginning by design, and if you actually start with the right material. And we'll finish with the road to commercialization. So at C12, we are focusing on developing a quantum core processor. So our quantum chip will be integrated into with a classical computer, and we will use this system to run hybrid quantum classical algorithm, where the quantum part will be minimized to avoid the limit of decurrence. And I think that that's a really interesting area of development and research, because for a long time we thought that we need perfect quantum computers to actually run useful algorithm. But now we know that we can run some useful algorithm also on imperfect quantum machines. And so this is exactly the direction that we are doing. And this will, especially actually for quantum chemistry. And so in 2025, this kind of application will probably represent the largest quantum computing market segments. And this corresponds to the NISQ. So now we are all familiar with the acronym Noisy Intermediate Scale Quantum. So it means quantum machine with a limited number of qubits and no error correction. This is what we are developing. And what we bring something very new to this field is the high quality of physical qubits. And so really first focusing on the quality and then the quantity. So starting after 2025, we'll scale the number of qubits, add error correction. And we have two main advantages for error correction. One is high quality physical qubits, and the second one is the connectivity that we can offer between them. So what if you want to test quantum algorithm before 2025? And here I'm really happy to announce that we will release our simulator next year. And it's a first-of-its-kind simulator because it's really a digital twin of our future quantum processors. If you are looking for a simulator available in current portals, you have either noiseless simulator, which are interesting in the long term, or noisy one. But the noisy one, they apply a constant error probability on each gate. What we have developed is that we have modeled all the physics phenomena that occur inside the hardware to that occur inside the hardware during the computation in our simulator. And I think this will be a very useful resource to test a quantum algorithm and also to understand and study the scaling law of quantum algorithm on our platform. And also 2025 is not that far away. So what we have developed is a very structured, step-by-step approach with forward-thinking company that want to be ready when quantum advantage will be there. So first is about identifying the use case, then developing the algorithm and testing it on a simulator, on our simulator, and the third one is developing the layout of the chip. So, of course, reach out to us if you are interested. And for example, we are supporting Air Liquide on his quantum journey. And I'm pleased to announce that we are developing the hardware part while we partner with Quantinuum on the software and quantum algorithm part. What I really like about this use case and that we have been able to identify a use case that is both relevant for near-term hardware, but also that has very high business impact. This is the optimization of atomic layer deposition. So it's a chemical process that is used in the semiconductor industry, and Air Liquide is supplying gas for the semiconductor industry. And customer, like TSMC or Samsung, they are interested in depositing new kinds of metals, especially because it's very important to achieve smaller technology node. But this actual chemical reaction involving the precursor is very hard to simulate. And Air Liquide is left by only experimental development, which take very long, which take years. And what we are looking with this project and to see if with our technology and with quantum computers, you can actually completely change this development time. So again, thank you very much, and happy to introduce you to our very unique and new technology. Thank you. Yeah, I keep a short time for Q&A. I think there is also some a mic here. So there is one question here. Hello.
What temperature do you operate at?
So we are operating at 15 millikelvin. So we have to actually get rid of thermal noise. So we are the same as superconducting, for example, platform. the thing is that what is different from superconducting is that our qubit footprint is much, much smaller than superconducting, so 10,000 times smaller, which means that even if in the long term we will have like 1 million qubits, the volume to actually cool down is much, much less. And we're not talking about a soccer field, but something that is much more treatable.
Thank you.
Tractable.
Any other questions?
So if there's no other question, and if I have like 1 minute left. Okay. No, so maybe also to give you also some more insight about where we are in terms of technological development. So it's still an early stage technology. But what achieved this year also is that we validate the 3 main components that are the core of our platform. The 3 main components are, of course, the host material, so the a single carbon nanotube. The second one is something that you can see as a controller of the spin. So it's a magnetic gate. And on this, we actually were able to fab like micromagnets just under the spin. And we also have some patent on more like sophisticated micromagnet. And this is interesting because this actually can benefit from any spin qubit platform. And the last component is a microwave resonator, and it's used to couple the different spin together. So you can see that as a communication bus in our silicon chip. And this will achieve state-of-the-art resonator with, in terms of quality factor. So it's good development going on. And thank you again. And I think I'm now at time limits. Again, thank you.